In this video, we're going to have an introduction to the Pythagorean theorem. So the Pythagorean theorem is one of the most famous theorems in mathematics, and in this first video, we're going to get a feel for how and why it works. So first, we're asked to find the indicated areas requested below, find the total area of figure A and figure B. So notice figure A and figure B are partitioned and shaded in different ways, but if we count the number of squares this way, or the lengths, 1, 2, 3, 4, 5, 6, 7, this has length 7, 3, and 4. This also has length 7. So the total area of figure A is 7 times 7, which is 49. Similarly, if we look at figure B, this is 1, 2, 3, 4, 5, 6, 7 units high, and 1, 2, 3, 4, 5, 6, 7 units wide. So it also has an area of 7 times 7, or 49 square units. So now we've established that figure A and figure B have the same area, and in the next slide we're going to look at these different partitionings and use the moving and additivity principle to try to draw some connections and conclusions. So now we're asked to find the corresponding areas in figure A and B and fill in the table below. So first we're asked to find the area of a pink rectangle in figure A. So here's figure A. Notice there's two pink rectangles. I'm going to add a little column here and note, I'll put number. There's two pink rectangles, okay? And the rectangles have one length of side 1, 2, 3, and another length of side 4. So this would be 3 times 4, and 3 times 4 is 12. And I'm going to make a total column. So since there's two pink rectangles with area of 12, their total area is 24. Now we're asked to find the area of the green rectangle. So notice this is not only a rectangle, it's a square. A square can also be called a rectangle, but a rectangle isn't always a square. So not a square, but this is a square. And it has length 1, 2, 3 by 1, 2, 3. So the lengths are the same size. There's just one of those. So its area is 3 times 3, or we can also write that as 3 squared, which is 9. Since there's one of them, that total area would be 9. Okay. Now we want to look at the orange rectangle. So we have 1, 2, 3, 4 by 1, 2, 3, 4. So this is also a square. There's one of them. And its area is 4 times 4, or 4 squared, which is 16, for a total of 16. Now we're asked to find the area of the blue triangle in figure B. So notice figure B has 1, 2, 3, 4 blue triangles, and notice even though they're rotated, they're all identical triangles. So this has length 3 and length 4, and it's a right triangle because this is a 90-degree angle. Here we have 3 and 4, 3 and 4, and this is 4 and 3. So there are 4 blue triangles, and each of their areas is 1/2 the base. We can look at any one we want to find the base. So we'll say 1, 2, 3, 4, base of 4, and a height of 3. So 1/2 times 4 times 3 is 2 times 3, which is 6. And since we have 4 of them, the total area of the 4 blue triangles is 24. Now we're asked to use the information in the table to find the area of the yellow shape in figure B. So notice we weren't asked to find the yellow shape in figure B. The sides aren't lining up exactly with the squares, the gridded squares, so it's hard to determine from this picture what its area would be. But we know the total area of figure A, and we know all of these pieces, so we can use the idea of the moving and additivity principles and subtracting to find what this area would be. Now notice that these two values are the same. So the 2 pink rectangles have the same area as the 4 blue triangles. Okay? Now this could just be coincidence, so let's see if we can figure out why this might be and if it's coincidence or if this is always true. So I am going to take these pink rectangles and I'm going to draw these diagonals and turn them into 2 triangles. Okay? I'm going to label our triangles here, 1, 2, 3, and 4. Okay? And now I'm going to see that I could take 2 of these triangles and it will exactly match a pink rectangle. So notice this has 1, 2, 3, 4 length this way, 3 that way, just like this rectangle number 1. This is 3 for this space and 4 for the height, just like rectangle number 4. This has a base of 4 and a height of 3, just like rectangle number 3. And this is 4 here and 3 on this side, just like rectangle number 2. Okay. Well, if these areas are equal, that means the yellow figure must equal the sum of these 2 pieces. So, the yellow shape is equal to, we'll put the green plus the orange, which is 3 squared plus 4 squared. And I'm writing it this way for a reason, you'll see why later, which is 9 plus 16, which is 25. So this yellow shape right here has an area of 25. Now part E says the yellow shape is a square. How can you tell this from figure B? Okay, so we don't know any of these side lengths right now, but we can determine this is a yellow square, or this is a square, and that all of these sides are equal, and here's why. So looking at all of these right triangles, we saw that they're all equivalent. They're not just similar, they're identical. We could move them. You could think about flipping this one to get this one, okay? And they're all identical triangles. Well, that means that since this is our right angle, this side is the side across from the right angle in triangle 3. That has to be the same as the side across from the right angle in triangle 4. And the same will apply for triangles 2 and 1. So now we know all these sides are equal. We don't know their length, but if all the sides are equal, then it must be a square. Okay, so how can we tell this from figure B? Because its sides are made up of corresponding sides of identical triangles. Okay. So now we know 2 things. We know that this yellow shape is a square, and we know that its area is 25. So in part F, we're asked, find the side length of the yellow square in figure B. Well, we know if we have a square that, just like we did here, the sides are the same length. So we have some number times that same number, so I'm calling them both question mark, is going to equal 25. Okay, so what number times itself equals 25? Well, we know that 25 is a perfect square. It's 5 squared. So that means that the number we're looking for, or the side length, equals 5. So the side length of the yellow square is 5 units. So, looking back at this piece of information, we can make a statement or an equation that says 3 squared plus 4 squared is equal to 5 squared. This was our 3 squared, this was our 4 squared, and this equals 5 squared right here. And this is a direct result of the Pythagorean theorem, and you can read about that result in your media lesson packet. And in 2 more videos, we're going to use the Pythagorean theorem and talk about it in more detail. In the next video, we're going to talk about finding square roots, because when we found what number times itself equals 25 here, using this method, we were actually finding what we call a square root. And we're going to need to use that idea to use the Pythagorean theorem.